welcome to the video. In the yesterday's class, we have studied about the basic introduction to heat transfer by radiation, and we felt that heat transfer by radiation, transferred by radiation is by virtue of its temperature. Then we also found out the definition for the black body, which is a hypothetical body, such that this hypothetical body can absorb the thermal radiation at all wavelengths, and then it does not reflect anything, okay? But it can emit thermal radiation in any wavelengths, okay? So it is the definition for black body. Then we have learned about the basic definition for the emission phenomenon of the radiation. So emission phenomenon is something to produce, right? Production of the radiation, okay? So there we also seen few terms like total hemispherical emissive power, which is we said E, where we said if there is some source, then this source will emit the thermal radiation in all directions. So you can say that it is geometrically defined as well as directionally defined, so that it will cover some hemisphere like this. And what happens is this, then we place some area like A, right, like this, right? So we can place some area of A, and then we count the thermal radiant heat flux, which is radiant heat flux, or you can say radiant flux, which is the heat, okay, that we are looking. And then we defined this emissive power. Then we also defined EB as the emissive power of the black body, such that our black body being the perfect body, our EB is always greater than E. Then we also defined one parameter called E lambda, which is the monochromatic. So I forgot to mention in first case, where when we define the total hemispherical emissive power, what I have said is that this source, which is S, will emit the thermal radiation at all wavelength. You can say all wavelength, okay? So if you just quantify how many wavelengths or how many radiant heat flux which is traveling through the area that you have taken without taking the details of the wavelengths, okay, you are just placing the area and then you are counting the wavelengths or the radiant heat flux which is at all wavelengths, then this is the total hemispherical emission power. Whereas E lambda is also called monochromatic emission power. Now, instead of just counting the radiant heat flux of all value of wavelength, now you are looking at the specific wavelength. So you can say your wavelength looking after is the lambda dash. Then you will ignore all the radiation which has the wavelength other than the lambda dash. So you will just count by placing some area, and then you will just count how many radiant heat flux which is with the area of dA, where your correspond to the lambda dash. Therefore, you can say that your E lambda is just the small part of the spectrum divided by the exact wavelength that you're looking for. Then you can say that your total dE, if you integrate this, and then you can say that this source can emit the wavelength, which is the measure of the distance, right? A sinusoidal wave like this, if there is the crest and the trough, right? Here is the crest. So if you measure this, right, so you can say this is the wavelength. So when you do that, when you integrate this whole over this, then you are getting E lambda, T lambda, and you are doing this, all of this like this, all of the above. Then you are just quantifying the value of E, which is the emissive power of the whole radiation, okay, whole wavelength. Then we defined two comparative properties, which is the epsilon and epsilon lambda. This epsilon is actually the ratio of the total emissive power of the source that you have divided by the emissive power of the black body, whereas this epsilon lambda is again the monochromatic emissive power of your source divided by the monochromatic emissive power of black body. So you can say that with this, so this epsilon term has the suffix emissivity. So you can say that this is the emissivity, like this, and you can call this as monochromatic emissivity, okay. Or you can say that when you confine this wavelength in certain range, then you are looking at certain spectrum, right? Therefore you can also measure this as a spectral emissivity. You can say spectral emissivity. Then we have also discussed about a few laws that concern with the emission. The first law is the Planck's law, where Planck derived from the quantum theory. What he has found is the expression for the monochromatic emissive power of the black body, which is EB lambda equals to, so he got some constant of C1, then it depended on the wavelength of the thermal radiation it emitted times the e raised to C2 lambda t minus 1. So here this C1 and C2 are the coefficients, and I also gave in the class the exact values, whereas this T is always the absolute temperature. So one of the things that you have to keep in this chapter is that any temperature you are dealing with are always the absolute temperature. So whatever degree Celsius or Fahrenheit or any different temperature unit you get, you shouldn't forget to convert to Kelvin, equivalent Kelvin scale. Then we have used this equation to find out the two extreme values. So it has given one Rayleigh-Jean's law, and it also has given the rise to Wien's law. So Wien's law, actually William Wiens, so he found out in experiment that the emissive power of the black body with respect to the lambda, then he found out that at the isothermal temperature he got some kind of this curve, so here like this, and you can say T1, T2 and T3, where my T1 is greater than T2 is greater than T3. So what he has got is that the maximum value of the emissive power, happened at different values of lambda. So at high temperature, your lambda max 1 is lesser than lambda max 2 is lambda max 3. So it dependent, this EB max at this each temperature dependent on the temperature as well as the wavelength. Therefore, he has found the empirical law that at any of this temperature, if he have taken the product of the max thing like lambda m1 times T1 is always a constant, which is 0.002898 meter Kelvin, and same thing lambda 2 times T2 equals to same thing 2898 meter Kelvin, like that. Then what happened is that you can see that the spectral, the lines here, the isothermal lines, has the property that whatever at the high temperature your EB max is obtained at a very low value of the lambda, whereas when you use very low temperatures, then your this one lambda m means lambda m value increases to give the lambda Emax. Then we have found out that the point where at certain temperature of T1, you can say T1, where when do we get the EB max, right? This is by using this Planck's law, and what did we do is we just differentiated like this, to get the maximum value of this. When we did this, we have got exactly the Wien's displacement law, 0.002898 meter Kelvin. When does the lambda B max takes place? Okay, so it takes place when our lambda max equals to 0.002898 divided by T, right? So when we do that, what happens is that when we substitute it in this formula, we got good relation that it has some constant C3 times T5, right? Whereas C3 has some value that I've given in the class. So you can say that at any temperature, certain temperature of this absolute temperature of T, our EB max is always proportional to the fifth power of the temperature. So you can say that our EBY max is strongly the function of the absolute temperature. Now, in this class, what we are going to do is, we are going to now find out that what is the emissive power of the black hole. By definition of emissive power of the black hole, or by definition, we have that E B lambda is actually dEb by d lambda. So to do that, what we have to say is that we are interested in finding dEb evaluated over whole wavelength, so 0 to infinity, such that we have E b lambda times d lambda, like that, from 0 to infinity. So this expression is what we have from the Planck's law, right? So we have is the C1 upon lambda 5 E C2 lambda t minus 1 d lambda is what we have. So our job is to integrate this from 0 to infinity. This infinity belongs to wavelength and 0 also belongs to wavelength. So what we are doing is actually the Wien's displacement curve. We have something like this, right? So from here it is 0 and we have infinity at some temperature of T. Then we have EB lambda of the black hole. So what we are saying is, we are trying to find out the area under this curve, which this function is given by exactly lambda 5 e raised to c2 lambda t minus 1. Now our job is to find this, and then this is very difficult integral to integrate. So in this method, we are trying to incorporate the substitution method. So what we are going to do is that I will do like this. Let x equals 1 over lambda. So when I do this, then I'm getting dx equals to minus 1 over lambda squared d lambda. So when I substitute these values inside this formula, now I'm able to get EB equals to, and then we also have to modify the limits, okay? So we have this one, lambda. We are saying when lambda equals to 0, what happens? We substitute in this and our x is infinity. Whereas when lambda equals to infinity, our x tends to 0. Therefore, the limits flip in this. Therefore, we are getting infinity to 0. If we substitute these values, then we have c1 times x to the 5th power, right, divided by we have e raised to c2 x upon t minus 1 times, now we have to find the value of d lambda. You know that our x equals to 1 by lambda, so x squared is equals to 1 by lambda squared. So what I can do is that I can substitute here this lambda squared by minus of x squared. So when I have this, then my d lambda equals to, I've shifted this and say 1 by x squared times dx. So in terms of this d lambda, I'm going to substitute this value here and say that it is now 1 by x squared dx. Now we can do some simplification here, saying x cube. Then we are now getting EB equals to minus of infinity to 0 x cube c1 upon e raised to c2x by t minus 1 times dx. And we can also write that if we have function of x dx from limit a to b, then we can write minus of f of x from b to a, right? So when I try to shift this, I will cancel this minus by flipping the limits, and then I will write as 0 to infinity once again as x cubed c1 upon e2 e c x upon t minus 1 dx. Now our job is to find the value of integral of this one. So what I can do is, this integral itself is again difficult to evaluate. So what I will do is, I will say EB equals to C1, say like this, 0 to infinity, we have this C1, don't forget, and we have now is x cubed times e raised to C2x by 1 minus 1 raised to 1 dx. So if you see this carefully, you can see that this can be expressed in the sum of the geometric term. Now you can see that this exhibits this some sort of geometric series, sum of the geometric series. So infinite geometric series with the first term a can be written as a plus ar squared, ar plus ar squared plus ar cubed, like this. If this is the infinite series, then this converges to a by a minus r, where r is less than 1, right? Here, if I say that my a, the first term is 1, then I can refine this and say 1 plus r squared plus r cubed plus dash dash dash, and it will converge to 1 by r. Now I have to modify this in this form, and then to do that I can say 1 divided by e raised to c2x by t minus 1. Okay, so for the simplification, what I can say is, I can say c2x divided by t equals to a. Then our expression has become now 1 divided by e raised to a minus 1, right? But here I need something like 1 minus of some number. What can I do to make this? In this case, I can say 1 divided by e raised to a, 1 minus e raised to minus a. So when I say this, I am getting this in some form like this, right? If I get this, then I can say as e raised to minus of a. I've shifted here, divided by 1 minus e raised to minus of a. Now I am ready to write down in this term as this one. So by expanding this sum as the infinite geometric series, I now get as 1 minus e raised to a by e raised to a equals to e raised to a. Then I'm getting 1 plus e raised to 2a, right? E raised to 3a, and so on. How is this possible? Because you can say that our whole thing, this one equals to r omega. So with this r, and if we square this r, then you are saying is e raised to minus a times e raised to minus a. If you cube this, then you are saying e raised to minus a times e raised to minus a times e raised to minus a, right? So you're doing this one, and then when you do this, and we have the same base, so you have to add the numerators only. Therefore we can write this whole thing as this one. E raised to b equals to 0 to infinity, we have c1 infinity, we have x cubed, then our e raised to minus a plus e raised to minus 2a plus e raised to minus 3a, like this, dx, where a equals to c2x upon t. So if you look very carefully, we can even write this in a summation form. So if you see this carefully, you can say that I can write in this. You can say e raised to minus of na, and then you can say n starts from 1 and ends in infinity. Now by using this result, now we can modify and we can write as 0 to infinity times c1 x cubed times the summation of n equals to 1 infinity of e raised to minus of na dx. Now job is to evaluate the value of this expression. So from the understanding that the integral of sum equals to sum of the integral, okay, this is the fundamental theorem. From here you can say, here what you are saying is you have integral of sum is equal to sum of the integral, which means you can take the summation out of the integral sign. So when you do that, I can say EB equals to now C1 in summation of n equals to 1 infinity of 0 to infinity of x cubed e raised to na dx. Now you are getting something familiar for this. You know that any integral running from 0 to infinity and involving this kind of form is called the improper integral. So we have very interesting result which involves this form. So we have something like 0 to infinity integral of something like that. If x equals to I, okay, then we have e raised to minus of, you can say some constant of k, then again x equals to, you can say dx equals to, this nicely converges to what? You'll converge to I factorial upon k n plus 1. So you have to be very careful to convert this form in this form. Okay, so first you have to see is that in this n we don't have x, but we know that a is equals to c2 times t, c2 times x upon t, right? And then we have this n equals to 1, 2, 3 something. So what we are going to make is that we are going to isolate this x and then turn this n inside to make this formula. So I can say, I can now take this as something like this. I can say this as c2 times n upon t times x. Then if I treat this as k, then I am making exactly this formula, right? So I will write like this, in this manner, in this fashion, as EB equals to C1 summation of n equals to 1 infinity of 0 to infinity of x raised to, we have x raised to 3 times here e raised to minus of, what is the value of k that we have set here, is n c2 upon t times of x dx, right? So if this is the case, then we can use this result and say now as c1 lambda n equals to 1 infinity, okay, then this whole integral will reduce to this one. So we have is I factorial. So what is the value of I? I is 3 here. So we are getting is 6 factorial divided by, what is the value of k? Our k value is n c2 upon t, right, times I, here is, you can see is I plus 1, okay? This is the mistake. So you can say I plus 1. Therefore, you can say is 3 plus 1. So this one equals to c1 lambda n equals to 1 infinity of, this one is 3 factorial. So you are getting 6 divided by n c2 upon t raised to 4. So now you are getting is just C1 n equals to 1 infinity of what you are now getting 6 T4 divided by n C2 raised to 4, and your n value is equals to from n equals to 1 to n equals to infinity, right? We have defined here our a value is defined here as you can see here as this term, where our a value 1 2 3 4 like this to make this term omega. So by doing this, what you are getting is now our ab value is, you can say c4 is also constant, so you can say as c1 6 t to the 4th divided by c to the 4th, c2 to the 4th, and summation you can see here as n equals to 1 infinity of your 1 by n4. So this is actually the Riemann zeta function, like with the value of 4. So we can say Riemann zeta function of 4 equals to summation of n equals to 1 to infinity of 1 by ns, like this, right, where our s equals to 4. So in this, then you can expand this series in the form EB equals to 6 C1 T fourth by C2 over 4th. You can expand this and you can say 1 plus 1 by 2 squared plus 1 by 3 squared, like this, right? And now you might be familiar of this series. So by using the Fourier series and the Parseval theorem, you know this series 1 plus 1 by 4 plus 1 by 9 plus 1 by 25 dash 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 nicely converges to pi raised to 4 upon 90. Okay, so you can check this, the result of the series. Then by doing this, you are saying EB equals to 6C1 t raised to 4 divided by C2 raised to 4 times pi raised to 4 by 90. Here you can see that almost all the terms are the constants. You can see 6 is a constant, C1 is constant, C2 is constant, and pi and 90 is a constant. So what you can say is, you can collect this all constants together and say 6C1 by C2 4 times pi 4 by 90, like this, times t raised to 4. And then this has the value of C1 times pi by 4 times C2 times 4 times 90. So you can get is EB equals to 6 times 3 times 7 4 times 10 raised to minus of 16. Okay, this is C1 value times pi raised to 4. This pi raised to 4 divided by C2. What is the C2 value? 1.438 times 10 raised to 2 raised to 4 times 90 times t raised to 4. You are getting this, the value of 5.670 times 10 raised to minus of 8 watt per meter squared per t raised to 4. So these are constant and this is denoted as sigma. And then if you denote this as like this and it has a value of this, then our equation finally becomes e raised to b equals to sigma times absolute temperature raised to 4. So this is the expression for the emissive power, total hemispherical emissive power of a black body. So this law is called the Stefan-Boltzmann Law. And this sigma having the value of 5.670 times 10 raised to minus 8 watt per meter squared T raised to 4 is called the Stefan-Boltzmann constant. Okay, so this is the Stefan-Boltzmann constant. So in nutshell, what does this gives is, it gives the emissive power, total hemispherical emissive power of a black body. Okay, so which will be in watt per meter squared, right? Because it is also the radiant flux, which is the thermal heat flow per second or per time per meter squared, right? This one is having this one, and this has the unit of this one, and you can see that this expression is what Stefan-Boltzmann's law is. And of course, this T raised to 4, this T is the absolute temperature. So this is in Kelvin. Okay, I hope you have understood this video, and then you just pause, and if you have any questions you can ask in the next class. Thank you.